And I'm glad to introduce you to my work I'm doing for my internship because so the development of this tool to assist the programmer while designing secure code. I work with through an introduction of the LADA and secure projects that are the context of my work, and then talking about the information leakage that is mainly the concern of the LADA project, and the reason of our choice to work with a compiler that is the main concern of the secure project. And then I describe you the tool that I'm developing, the bit slicer, and the future development of the secure project itself. So now, the other project that is run by the cryptography research group of the University of Bristol is focused on studying the information leakage of the digital devices. Devices such as smart cards or smartphones, so devices we use every day, against a quite sophisticated kind of attack that is the so-called side channel attacks, the term that you may be familiar with. That are attacks. Sorry for that. Attacks that don't rely on weaknesses of the algorithm used to encrypt the data, but rely more on intrinsic characteristics or features of the devices, such as physical characteristics, such as the power consumption, the time and behavior of the program that encrypts the data, and also electromagnetic emissions, and also even sound emission of the devices. So what is the concern of this project? Is that in order to test a new device or a new implementation, a new algorithm against these kind of threats, you need a well-equipped lab and also some expertise in the field. For instance, someone who can design a proper test or and run it, of course, to be sure that the implementation is strong against this kind of threats. And so the project, the lab project, aims at delivering and making available this the power of a well-equipped lab and expertise to any programmer who's trying to develop this kind of code without the need from the programmer to of a specific knowledge about the subject. And the secure project instead, that is quite young, since it started at the beginning of July, is more focused on the development of tools for the compilers, in our case LLVM and GCC, that basically do the same thing, such as that is support and help the programmer with the implementation of secure code. So what do we mean when we talk about information leakage? We are talking about, as I said, digital devices, as I was saying before, and these kinds of threats. So attacks that address this intrinsic characteristic of the devices. And to give you an example, just to understand better, this is an example taken from a crypto library, the Polar SSL library, but don't worry, it has been fixed a lot of time ago. It's quite an old commit. Anyway, you can see in the first line the pointer that is going to address the buff variable, and the buff variable contains some secret information, but then they're using the pointer p in a condition of an if statement that once the condition is satisfied will make the function return a value. So here, this is an example of a side channel introduced by a bad practice, that is by using a variable that is related to secret data to control the flow of the execution flow. And this could give a clue to a proper tool well designed to measure this kind of the differences in the execution time to understand what is the content of of buff in this case. So what are the secret data that they are processing at the moment? So why are we working with the compiler? First of all, as we all know, compilers are already well tested and designed tools to analyze the code, because they go through almost each line of the program, and they give us the possibility to analyze and transform the code. That is basically what we are trying to do with these tools. Let's take, for instance, again the compilation process. You can see here I don't need to tell you about this, but you can see here the source language that goes through the lexical analysis, syntax analysis, the semantic analysis, and then is turned to an intermediate representation, to which is applied by the backend optimization before generating the code. And that's the point in which I'm working, basically, the optimization phase on the intermediate representation of the code. And that's where my tool, the BSlicer, acts. First of all, I don't know if we are all familiar with the concept of bit slicing. Historically, bit slicing is a term that was used to refer to the practice of building a processor with a word of certain length by using processor with shorter words in parallel, let's say. So I could build an n-bit processor by using n 1-bit processor working in parallel. In software instead, this concept implies dedicating, let's say, a virtual register, so in our case at least a byte to each bit of the original data. And in let's say, an orthogonal representation of the data that I will explain you in a while. And of course, this implies also that all operations performed on this data have to be orthogonalized as well. What do I mean by orthogonalization? Here you can see on the left the array that we mean to be sliced. And on the right, I put it vertically just to give you a better idea what this process is about. You see that I put each bit from that array in the first place of each byte of a new array. So there has been an expansion of the space used by the process, and a division of the bits for which was allocated one element per each. Okay, and why is this necessary? In what fields? In cryptography, for instance, this kind of practice lets the programmer more easily create a constant time execution regardless of the input. What does it mean? Let's imagine, for instance, block ciphers. I think we are all familiar with the block ciphers anyway. Let's take into account all the operations that perform on the input. In an encryption scheme, it's a key feature that the execution time of the encryption does not depend at all on what is the input. But if we were able to transform these operations into atomic Boolean operations, we are more sure that there's no more this dependency, because, as you may know, an atomic Boolean operation, according to about execution time, it does not depend on the input. The execution time of an atomic Boolean operation does not depend on what is the input. So if we manage to slice the data and then besides also the algorithm applied to this data, we should reach a constant time execution that does not depend on what is the input, so what is the secret we are trying to encrypt. And moreover, this technique particularly suits cryptography because, and block ciphers above all, because as you have seen before here, we are allocated some space that may be unused. I'm talking about all the bits that are not using in the array on the right, that can be used in a block cipher to host other chunks of plain text taken just all in parallel and compacted in a new version of the data. And since block ciphers perform the same operation on each block of input they take, we can, once we slice also the algorithm and we obtain this atomic Boolean operation, we can perform these operations on all the bits of one slice. By slice, I mean one of these elements, that is the set of the bits coming from the same position from each block that was an input. So here was a brief explanation of what block cipher is, just in case anyone is not familiar with that. We're talking about a deterministic and invertible transformation of a fixed length group of bits. That's what let us adopt a technique such as this technique of using more blocks in parallel, and since it is deterministic, apply the same operation on all the blocks that we are processing. Here I put a couple of examples of orthogonalized algorithm. Well, if then anyone is interested in getting this slide, there will be these links. Anyway, the first example, using a bitSlice version of an algorithm to encrypt the data, to introduce some redundant bits to make the code stronger against the fault attacks. While the second example is about let's say a constant time version of the AES algorithm, and takes into account also the increased efficiency brought by processing more input at a time. Okay, so yeah, but yeah, this slicing may sound appealing, but is not so well a widespread technique because it's quite niche. I mean, as you have seen, it implies an increase of allocated data, of allocated space, sorry, and also an increase of the code used, because you need to manage all the slices and all the relocation of the bits. But also, it requires the algorithm to be suitable to be orthogonalized, let's say. Not all algorithms are suitable for this purpose. Think, for instance, about a block cipher that just performs bitwise operation of the input. Bitwise operations are really easy to orthogonalize because you just need to perform the same operation on each bit instead of each byte as it was in the original version. But if, for instance, there are more complex permutations, well, things become a little trickier, let's say. But if this is your case, your ideal case, and you think that your algorithm can be efficiently orthogonalized, then you may consider using a tool like the bitSlicer that, once it will be implemented as a prototype, will provide some tools to annotate, for instance, some of the parts of the code that the programmer wants to be bitSliced. And then we'll do the dirty work of bitSlicing this data, so orthogonalizing the data and consequently the algorithm itself, without the need from the programmer of managing this bitSliced format of the algorithm. So here, for example, let's see how a programmer would like to encrypt his function. If, for instance, I just implemented my function to encrypt data, I would like to make the tool, make the compiler actually bitSlice it. So I just need to add an attribute to the definition of the function, and then the compiler would do the dirty work. Let's say here is an example of what kind of transformation I mean. On the top you can see a simple XOR operation between all the blocks of the plain text in input and the corresponding keys. Possible orthogonalization of this of this practice would be to, of course, to perform the same store operation, but by taking each time a different slice of the bit slice version of the plain text. That is, basically, instead of applying the XOR operation between each element of the plain text and each element of the key, you just apply that operation to between each slice of the bit slice plain text and each slice of the bit slice key. That basically balances the loss of efficiency. One other idea I had about this tool is that to leave the freedom to the programmer to manage the bit slice data. But how? Since our aim is to make that easier to programmers. For instance, the bit slicer could bit slice the data, the needed data, and then provide the user with some tools such as this function to access the slices, because the access to the slices is the key point in cryptography or in this kind of situation in which we have bit slice data. And the bit slicer would keep consistency also with not bitwise accesses. Sorry. And that is basically what I mean. Let's suppose, for instance, that we are assigning not this slice value, if you understand what I mean, to the plain text that we are told the compiler to bit slice. So basically, the user just needs to do what he needs, and then the bit slicer detects this assignment of a not bit slice variable or value to a bit slice value, and so it just bit slices temporarily the value and stores it at the corresponding location. In this example, you see that the assignment regards the second block, according to this this example. Sorry, the third block, the input, and the first element. So, as you can see here, the bits of the value are put at the third position because they are above the third block in input. On the other hand, if a programmer wants to assign a bit slice value to not bit slice variable, of course, the bit slicer will detect this and rebuild the value stored as a bit slice value just to be able to insert it in that instruction. These are quite simple examples of more complex operation, of course. But basically that's how the bit slicer could keep consistency with all other parts of the algorithm that a user that is actively using the slices wouldn't expect to have to do with. Alright, so some other developments of the secure project involved the introduction of some warnings, warnings based on a proper analysis of the code, and that aim at revealing some bad practice, such as the one we've seen before, such as using a variable that is related to some secrets in a construct that controls the flow, the execution flow. So in such a situation, the compiler will detect the presence of that variable in that condition and emit this kind of warning. As you can see here, we have also annotated the variable with a critical attribute, just to let the compiler keep track of this variable and also about all other variables addressing it, such as a pointer, by spreading the attribute through the instructions, and then so emit a warning whenever this variable is used in a not a proper place. I mean, And another aim of this project in the future will be the so-called stack arrays, that is the deletion, so erasing sensible data left in the stack. What do I mean? Let's think, for instance, about some functions that are managing some secrets, and put the secrets in the stack. Then the function returns. But if those secrets, so I'm talking about this word in the stack, the dead beef. Since this secret has been put in the stack, it could be possible, and again with the proper usage of pointers, to recover it. So just to be sure that this doesn't happen, I would like the stack to be erased once this kind of function that should be marked properly returns, in order to avoid, any attacker from recovering this data. So yeah, basically this is my work at the moment. It's still at quite an early stage, so I'm really open to any piece of advice you would like to give, but also to any question that I'll try to answer, of course.